I want to, first of all, thank you all for attending this webcast. Um, Originally, when I was trying to come up with an idea, I just put down that I'll do a few concurrency patterns, or I'll do some concurrency patterns, but I realized that there's a million of them out there, so I've amended the title to say a few concurrency patterns, so whatever we can get it to in an hour. This is going to focus on, obviously, .NET. So a little bit about me. My name is Pinku Sarana. That's my email if you have any questions or anything after the class or after this this webcast. And my job is I'm one of the instructors at Developmentor, and I mostly teach C Sharp and then various libraries within .NET within the .NET framework, design patterns. And then I teach a class on distributed architecture and design, and that's where this material kind of fits into that class. And the goal of this class, the distributed architecture, is when you're building real systems at work, where you have, let's say, multiple batch systems, where you're processing, millions of records. How do you build out big systems that can scale and that are reliable and are still flexible enough for you to modify and extend? All right, so let's move on. Let me see if there are. Yeah, okay. All right. So when we get to when we talk about concurrency in .NET, the thing is that Microsoft made a major, massive, huge improvement in the foundational layer of their concurrency library. So, obviously you have threads. Oh, somebody is saying they cannot see my screen. Oh, son of a bitch. All right. Okay, thank you for posting that. I had switched to the main screen to communicate with our tech admin. All right, thank you. I'm not that technically adept. Okay, so anyway, here's the slide that you missed about me, Pinku Sarana, my email, sarana@develop.com. So if you have any questions, feel free to ask. Okay, so the idea here is that obviously there are threads. Java has threads, C++ has threads, but there are many languages that don't have threads. For example, Python and Ruby and Node. These are languages that don't really support threads. They have another way of dealing with concurrency and parallelism, but it's not real threads. But working with real threads it's extremely, extremely difficult because you need to get two things right. You need to get it correct, and correct means that you don't have any deadlock issues where two threads, they want to get something, but nobody's releasing it, and so they're stuck waiting forever. And then there are really subtle behaviors like you're trying to read some data, but somebody's trying to write data at the same time, and so the data that you read can get corrupted. So of course, you know about locks, about all the various kinds of concurrency primitives that you can have to try and control this madness. But really, it's extremely, extremely difficult to get it both correct and efficient. It's easy to get one of those. I mean, I can write a screamingly fast program that crashes every 2 minutes. And it's easy to get correctness by just slapping a lock everywhere. Your program will run, sometimes it'll run even slower than a single-threaded program, but it's correct without being efficient. So even great programmers, people who are 100 times better than I will ever be, even they are scared of writing threaded programs because it is, as I said, so difficult. And so that's where this thread pool library comes in. With threads, you can do anything. With the thread pool, they're now confining you to a a very flexible pattern, but still it's not as robust as just using threads directly. So with the thread pool, what you do is uh, you break up your work into smaller chunks and you feed it into the thread pool. So you create these tasks, and that's where the system.threading.task library is in .NET. You create these tasks and you put it on a queue, the input queue. And all of this, by the way, in this thread pool library, is just a black box that you can't control. So, it lacks flexibility. I mean, there are all kinds of things I wish I could do, like why isn't this a priority queue? And, why can't I cancel task a little bit in a smarter way or whatever? But, you know, overall, it's pretty good. So what you do is submit a task, it's put on a queue. There's a thread pool library here that pulls off your task and hands it off to then stuffs it onto a worker queue. So this is a local queue that's managed by a background thread. So the thread pool library allocates a whole bunch of these background threads. It actually starts with a very small number, and if you start to use it a lot, it will expand and grow to some maximum size, which you can configure. And then if you stop using it, like let's say you're done with some huge burst of activity, then after a while the thread pool will start to release some of those threads. So it is a dynamic system that grows and shrinks based on demand. And the thread pool, is written to make maximum use of your hardware. So if you write a program that utilizes the thread pool on your laptop, which maybe has 2 cores, it'll work fine. And if you take that exact same program and drop it onto some huge beast of a server, the thread pool library will automatically expand out to use all of the hardware. All right, so it's a really great way of writing a simple program and having it automatically adapt to the hardware that it sits on. I mean, this would be much, much, much more difficult to do if you were managing threads yourself, because you would have to constantly ask, I forgot what it is, but some environment variable to ask how many processors do I have, and then write your program to, allocate that number of threads plus some extra and manage them all. So this is a huge, huge. What is it? It's immensely easier to do than regular threads. Now, one of the things that they made a big change in is that this thread pool has always been there in .NET. But what they did is they implemented an algorithm called work stealing, and work stealing is a special kind of thread pool that is optimized for CPU intensive tasks. So what this means now is that you can actually do number crunching and throw it into this thread pool, and it will be really efficient. You couldn't do that in the old thread pool. I think this came out in .NET 4. So prior to .NET 4, you couldn't do that because that thread pool was a much simpler implementation that was optimized for waiting around for I/O. Okay, so most of the time those threads were just waiting for a socket or a file or somebody to deliver information. This algorithm, the work stealing algorithm, is implemented in Java, so they have the same thread pool. Intel offers a library for C++ that does the same thing, and I'm not sure if I try not to follow any of the C++ stuff, but I'm not sure if Microsoft implemented a work stealing thread pool for C++. But regardless, it's widely accepted as probably the best implementation of thread pools right now, this algorithm. All right, so the thread pool then dumps work into these queues. The background thread takes takes a task off the queue, executes it, puts the answer in some safe area that you can access later on, and then gets the next element. And what's cool about the worker queue is if one of the background thread is working on a task, but the task is taking a really long time, then another thread who has already finished off his queue, what he can do is reach over to the back of the other guy's queue and say, hey, if you're not going to do this work, let me just steal that work and put it on my queue, and then I can get it done for you. Okay? So it's basically a smart form of load balancing, but it's extremely efficient. All right. Now, I'm not going to talk about tasks because there's a lot of information about tasks out there. What I'm going to talk about then is another concurrency pattern that is built on top of tasks. Tasks now are sort of the foundation of doing concurrency on .NET, sort of the easy way of doing it. So, for example, plink, which is the parallel version of LINQ, will break down your complex LINQ queries into a bunch of tasks and submit it into the thread pool so that you can do a parallel LINQ query. I'll show you this later. You can do a parallel LINQ query that breaks down a problem and then executes it all very efficiently across all of your cores. But what I'm really interested in talking about is the data flow stuff. So the data flow is a library that is put out by Microsoft. However, it doesn't come as part of the regular installation. Instead, you have to go to NuGet and do a search for, I think, tpl.dataflow, and you can install it into your project. So once you have it installed, what the data flow does is it says, let's think about your program as a network, okay, like a circuit diagram. And it's really for doing streams, data streams. Now, the data stream can be infinite. For example, if you're listening to Twitter, you could just have a process that sits there and says, listen to this infinite Twitter stream and do some processing. Or it could be, a finite stream where it says, I've got 1,000 records that I just pulled up from the database, and I want you to process all of those 1,000 records. Okay? But what's interesting about this sort of data flow is that it's a way of writing modular programs that are still parallel. So each one of these P's, these are processors, not processors. Let's just say they're a chunk of code. Okay, so it's a little chunk of code sitting here, another little chunk of code there. Okay. And as the stream of data goes in, it's being fed into a queue that this processor can operate on. So this processor will get each item off of the queue and do something with it. Now, in this example, it's going to produce an output. Okay, so the processing node will take a Twitter stream, a single tweet, right? And let's say it says, well, I'm only interested in tweets that are from North America. Okay. So this processing node right here, what it will do is take a tweet, look at the location, I think it's called the location tag, and make sure that it's within North America, and then forward it to the next element in this network, right? So the data streams flow over here. You can also split the stream in various ways, which I'll show you. So as the data flows in here, it gets pumped. This gets pumped into P3 and down into P4. And you can do that in a number of ways, okay? And then P3 and P4 can operate on the data that they get. And you can also do joins here. So the data from P3 and P4 gets merged together and you output a result. So this is obviously a super simple thing here, but it can be expanded into all kinds of complicated networks. Now, where this is interesting is that each one of these P's, these little nodes here, are actually running as a task. Okay, the implementation is going to be as a task, and you can actually tell it, I don't want just one task here. I want you to have, a maximum of 5 tasks for this processing node. So as the data gets fed in here, the first item goes to task number 1, the second one goes to task number 2, 3, 4, and 5, and then it stops. All the other ones get buffered, and when those tasks are finished, they push the result down to P2 and reach out and get another one. And in fact, you can say unbounded. And by saying unbounded, you're saying by saying unbounded, you can say that this can use as many tasks as you need in order to process that data stream. Okay, so that's where the parallelism comes from. So if you were to implement this network and have it running in on a big machine, this network would utilize all of your cores, all of your processors, all of your cores in order to process data as quickly as possible. Okay. Let's see. Somebody raised their hand. Let me see. We have a question here. What is the difference between a task and a thread? So a thread is, whoops. A thread is an operating system level resource. Whenever you run a program, the first thing it does is it creates a thread, and that's where your program is executing. So the only way to actually execute anything on your computer, there has to be a thread. Okay? So it's just an operating system level thing. Threads run inside of a process. A process is like a container that says, here's all the stuff that you want in order to run. You need some memory, you need some file handles, you need some sockets, whatever you need, the process will hold it and protect it. So it's also a security thing. Then inside of that process, the operating system will give you a thread, or you'll request a thread. And the thread then is what the operating system looks at and says, I'm going to take these threads and run them on the CPU. Okay? So that's all at the operating system level. A task is just let's say like a .NET object. And it's a .NET object that says, here's the function I want to run, and here's the data related to that function. So like if I want to add two numbers, and the two numbers are 1 and 2, okay? And so this thread is running a little program that says load the task, execute that function, put the answer somewhere, and then go back and get another one. Okay, so the difference then is a thread is a real operating system level thing that runs on your CPU. A task is a .NET object which contains the function you want to execute and any data that needs to go along with that function. Okay, so the operating system doesn't care about task at all. Task is just a programming thing. Just like if I were to create, a class for a dog or a cat or whatever, the operating system doesn't care. The computer doesn't care. They only care about these threads, and these threads then will load the task and execute them. Okay, hope that helped. So these data flow then create all these tasks and run them. And so, once you organize your problem into a data stream or into a data flow, you just start pumping data into it, and all of this stuff will start chugging along. And in fact, all of these things are going to run at the same time as data flows through there. So one element gets hit here, then it goes to P2, then it'll go to P3 or P4, and then it'll go to P5. So all of these things are being executed concurrently. So here are some examples of the kinds of blocks, these little nodes that they give you in the Dataflow library. They actually give you a very limited set of blocks, which is kind of disappointing. But you can always create your own, and it's actually not that hard to create your own. So an action block, if you notice, it says, if you give me data, I'll execute some action. But there's no output here. So I'm going to use this to write out our results. So the action block for me is going to execute a console.writeLine so we can see what the answers are. Transform block is what you'll use most of the time. It says, if you give me a data element, number 2, I will do something to it, and then I will shoot the answer out the other side. Okay, so there's a number 4. So this transform just takes the square of the input. So 2 goes to 4, 3 goes to 9, 4 goes to 16. Transform many block. This is a little bit more complicated. It says, if you give me an input value, and by the way, these inputs can be anything. This could be, for example, what is it called? A record set. Okay? So you you pass in a record set, and what this thing does, it says, I will send out a whole bunch of other things. So like in this example, I passed in one whole string, and the output is going to be a bunch of characters, So it splices up that string and shoots out a bunch of characters. Like if you gave it a record set, which has like 1,000 rows in it, then the output might be objects that represent each row. So this could be like in an ORM or something, right? So you give it a record set, and out comes, product number 1, 2, 3, 4, 5, like that. These are grouping blocks. So the batch block, what happens is you tell it, I want you to read these inputs that are coming in. So somebody is sending in the values 1, then 2, then 3, then 4. The batch block says, I want you to group the inputs by some number. And you tell it, I want groups of 4, for example. So this thing will just wait until it gets 4 items, and then it will spit out an array of 4 elements. Okay? A join is a way of merging 2 different outputs. So if somebody were to pass in a 2 and somebody were to pass in the character A, the join block would put these 2 together, like glue them together, and send out a tuple with a 2 and then A inside of it. Okay? And then the batched join is a combination of batch and join, obviously, hence the name. And what it does, it says, again, you tell it, I want you to group these into chunks of 4. So when you do that, somebody passes in a bunch of inputs here and a bunch of inputs there. The batch join says, okay, I'll produce a tuple which contains an array of 4 elements here and an array of 4 elements there. Okay? So the batched join, the batch really, and the batch join, these 2 things are used as an optimization sometimes, especially when you want to, which they don't support this, but if you wanted to add it, like if you wanted to send data to another machine, you don't want to send it one at a time because the communication overhead is pretty big, in general. And so it might be better to group it, and say, well, when I get, 4 or 10 elements, then, put it all into a collection and let me send that to another machine. All right. And now we have buffering blocks. Hang on. Yeah. And buffering blocks, basically, as you start passing data in, the buffer block can actually hold the data because, as it sends data out, it has to wait for somebody to read it. And if those guys are busy, they're not going to read it. So what do you do with those values? So we just buffer them here internally. So you can keep sending data in, like 1, 2, 3, 4. The buffer block will store it internally, 1, 2, 3, 4. But then when somebody reads it, it'll send out 1. The write once block is a way of dealing with constants. Because when you set up these networks, you want everything to be part of the network. Sometimes you need constant values in there, just as a way of modeling it. And so here you just write one value 2, and now anytime somebody reads from this block, they'll always get the value 2. The broadcast block is a little bit funnier. Whenever you write the value 2, it holds it locally. And then when people start reading from it, they're all going to get the value 2. 2, 2, 2, 2, 2. But then when you write a new value to it, like 3, then that updates the internal variable. So now when people read from the broadcast block, they'll all get the value 3. So this is a way of doing one-to-many broadcast. So think of it as a unicast in networking terms. Whoops. All right. Now to connect the blocks, well, okay, so not just connect, but these are various operations on the blocks, and then we're going to get to some code. So to parallelize a block, by default, when you create one of these blocks, it only will run one element at a time. So there's no parallelism going on, okay? So that's the default. If you want to turn on parallelism, then you say there's a second parameter to anytime you create a block, and you say new execution data flow block options, max degree of parallelism equals, And you can just give it some number, 1, 2, 3, 4, or you also have this option which says unbounded. Create as many tasks as you need. Okay, so you can play with this number to try and optimize your throughput on your network. To connect a block, like in order to create one of these diagrams, what you have to do is say P1 dot link to P2. All right, so you see this? Oh, I forgot to update this. Darn it. Okay, so link to target, and then there's an optional set of, options, but a really important one, which I'll talk about in a second, is propagate completion equals true. Okay, and let me just talk about this last one real quick, and then I'll talk about this filter when we do the example. I forgot to put the filter there. Okay, so when you're finished, like let's say over here, I'm going to pump in 1,000 records into this network, and then watch it all go through, and then get my results. Okay, so there needs to be some way to tell this processing node that you're finished. Once you've put in 1,000 elements, then you want to say, hey, I'm done with this thing. So what you do is you say P1.complete, and that tells P1, don't accept any more data and shut yourself down. Okay. Well, it shuts itself down only when it's done processing whatever is on its buffer. So that will get done, and it will send all the data to P2, and then it will shut itself down. However, we don't actually want this network to shut down until all of the nodes are finished, right? Because if I shove 1,000 records in here, I want to wait until I get 1,000 results, right? And you don't want to use a counter because it might be 1,000, it might be 2,000, it might be 112. You don't know. So what we do is we say propagate complete. So whenever P1 is finished and we call complete, P1 will then say, hey, I'm done, and it will tell P2, I'm finished sending any more messages. So that way P2 can finish up its buffer, send the data to P3 and P4, and then close itself, and then tell P3 and P4, don't expect any more information from me. Okay? And that's what propagate completion means, is that when you tell P1 to finish, it will tell P2 to finish, which will tell P3 and P4 to finish, which will tell P5 to finish. And so when you look at a network like this, you say P1.complete, and then you wait until P5 is finished. And you do that with this command. The last block, whatever it is, .completion.wait. So you can wait until the last block is finished processing all the data, and then you know that the network is finished and all of them have shut themselves off. Okay? All right, so let's look at some code. All right, well, I've already written a bunch of things, so let me just, it's already 1:30, so let me just show you what I've written so you can see real examples. So here is a here's a simple flow. In this thing, I'm going to create a start block, and all right, well, what I'm going to do here is I'm going to shove in the numbers 0 to 9 into the network. The first place it goes, so in order to send the number into the start block, whatever the entry point is, you call post. There's also like a send async, which will work nicely with the async await commands in C#. But post is simple enough. So what we do is we say put this value I and shove it into the start block, whatever that is. Okay. So the start block is a buffer block. Remember that it just loads up data, it stores it, and it tries to give it to the next guy in the link. The next two items I have are even and odd. And the even and odd are both transform blocks. So you can see here, new transform block. It takes an integer as an input on the input queue, and it sends an integer on the output queue. And here's the action that you want to perform. So it says, whenever I get an integer on the input queue, I want you to execute this operation. So the even numbers are going to get squared. okay? I mean, I just made it up. It doesn't matter. Whatever you want to do. So I times I is going to get squared. The odd numbers, it says, give me an integer, and I'm going to shoot an integer out. And that means, given a number, I'm going to add 1. So for no reason at all, I'm just going to add 1 to all the odd numbers, okay? So what I do is, if you take a look at this first line, I need to connect the start block with the even and the odd, because what I'm doing here is I'm trying to create 2 arrows. So the start block will send data to odd and to even, like this. That's the goal. So it says start.link to even, okay? And over here it says start.link to odd. Now, the buffer block, it's only going to send data to one of those, the even or the odd. And so the last option over here is what's called a filter. And it says, give me a predicate. And if the predicate returns true, then only then will I send it to the even block. Okay, and if this predicate returns true, only then will I send it to the odd block. So here, this predicate says, well, if I do modulo division by 2 and the remainder is 0, then it must be even, so return true. And if it's not equal to 0, then it must be odd. Okay, so with these filters, all the numbers now are going to get split up. Some of them are going to go to even, some of them are going to go to odd. And notice then with each one of these things, I always set propagate completion equals true. Okay? Now, both the even and the odd are linked to a join block. And if you remember, here is like what a join, here's how a join looks, is that we have even and odd, and they're both going to merge their data into this join block. So here we say even.link to join. Now, the join, there are 2 kinds of joins. One has two inputs, and another one has 3 inputs. Okay? So I'm using the one with 2 inputs, and you have to say explicitly that even is going to link to the first input on the join. It's exactly like trying to wire up circuits, And odd is going to connect up to the second input node on the join. Okay? And then the join, so that you see here is a join block. The join block doesn't do anything. All it does is says grab these 2 data values and merge them into a tuple. And then the join finally is going to link to the output. Here's the output. The output is an action block which takes a tuple of 2 integers as input. Why is it a tuple? Because that's what the join block is going to give me. So given this tuple, I'm just going to write out item 1 is this, item 2 is this. Okay? And now when I run this program, it's going to go through 0 to 9. It's going to post a number into the network, and then I'm going to tell the start node that I'm finished, and then I'm going to wait for the output node to be completely done before I say I'm done with the flow sample. Okay, hopefully that made sense. So let's come over here and do flow. And now I'm going to run it. Hopefully it doesn't crash. All right. It's not the most exciting thing in the world, but basically what happens is the number 0 went into the even, and the number 1 went into the odd category because it got 1 added to it. So 1 plus 1 is 2, right? And then the next one, 2 went over here and it got squared to 4, right? Here the number was 4 and it got squared to 16. The number was 6. The number was 8 over here, right? Whereas over here I got odd numbers. 1 plus 1 is 2. 3 plus 1 is 4. 5 plus 1 is 6. 7 plus 1 is 8. 9 plus 1 is 10. Okay? So all it does is show you that the network actually works. Data is flowing through, Okay. Let's see, 135. Okay. Let's see. Hang on a second. See some hands going up, but I'm not seeing the questions. No. Okay. Let's see. Let's jump ahead to this example for Twitter. Now, this is a little bit more complicated, and I can post the code on a shared drive somewhere. Let's see. Well, for now, let me explain what's happening. So what I'm going to do is I'm going to connect to Twitter, and I'm going to grab a stream of tweets. Okay, and what I'm going to do is something called sentiment analysis. Now, this, of course, is a demo, and so therefore, this is like the worst sentiment analysis job you can do. Sentiment analysis is what that means is what the machine will do is look at the tweet and figure out, are you feeling positive about this subject or negative about this subject? So it's trying to figure out how you feel about something. Okay, and people use this. Like there's a hedge fund in New York a few years ago that got started, where what they did was they analyzed the Twitter feeds on different stocks. Like they would follow like Microsoft, for example, and they would say, if the general feeling is positive for Microsoft, then we'll invest. Or at least that was one of their signals that maybe they should invest. And if the general feeling was negative, then maybe they would sell, right? And so what we need is some way of figuring out, how do people feel about this? Now, like I said, this field has gotten very advanced, with machine learning and all that. So I'm doing the drop-dead simplest thing you can do. So one of the guys in this field, what he did was he amassed a collection of words that tend to be negative. So here's negative words. And here's a collection of words that tend to be positive, right? So acclaim, admirable, adore, let's see, amazing, right? Like if somebody says something is amazing, probably they're being positive, unless they're saying, well, you're an amazing idiot, right? And that's what, like the newer sentiment analysis things, they can actually deal with a problem like if you say you're an amazing idiot, then they would know that that's negative. Whereas with the system that I'm doing, it's really pretty stupid. But it's neat, and we'll see if it works. All right, so they're just word lists. And now I'm going to, so in this first line here, with negative words and positive words, what I'm going to do is say file.readlines, and I put it on my desktop. So take these two files and convert them into a dictionary, because I want to do fast lookups, right? So now I get two dictionaries. I get a dictionary full of negative words and a dictionary full of positive words, okay? And then this delimiters is just it's a collection that has all of the characters that one would use to separate words. So like a white space, a tab, a period, a comma, that kind of thing. So any white space or any kind of punctuation, right? That's what's in the delimiters. Because I'm going to use this to break up the tweets. Okay, now, now in order to transform these tweets, I have a bunch of these blocks that I've put together already. And I'll show you how they work in a minute. But you see a transform block, another transform block. Here's another one, another one, another one. And then I have a join block. and an action block. And I also have what's called a broadcast block, okay, which I explained in the slides. Now, what I'm going to do is down here, I'm actually using a library called Link to Twitter, I think is what it's called. Yeah, Link to Twitter. And it's a really cool library. I was having some trouble with the async await stuff, so I just cheated. But anyway, what this thing is going to do is it says, go and connect to the streaming input from Twitter and filter it. So, so all of these tweets are going by. I want you to filter it and look for Justin Bieber. So I'm just going to search for Bieber, right, or the Biebs, and select out the streams. Okay, so this is like if you did a search in Twitter and got a bunch of tweets, that's what's going to come here. And then what this is going to do is post the content of each individual tweet into the head of my network, the start node for my network, which is called the JSON parser. Now, on Twitter, all the data is represented as JSON objects, and so. And it's got a whole bunch of fields. It's a huge object, okay? And all I want is the text inside of it. So we're going to go through a couple of steps here to extract the data, do the analysis, and output it. So this will take the string, or actually the entire JSON string, and shove it into the head of the network. It's going to only do 50 tweets, and once it's done, it's going to tell the JSON parser that it's finished, and then it's going to come down here and wait for the output results to be finished. Okay? All right, so the first step is the JSON parser. Now here I'm using another library, which is on NuGet, called newtonsoft.json. And I'm using it because it was the first thing that showed up when I did a search. All right. So the JSON parser is going to be a transform block that says, given a string, remember, this is going to be the entire JSON string, which is really big. It's going to create a JSON object. This is what comes from that library that I just showed you, the Newtonsoft library. And let's see, I had some debug junk in there, which I'll get rid of. And it's very simple. All it does says parse the string and convert it into a JSON object. Okay? And then on all of these things, on this one, I set the max degree of parallelism equal to unbounded on the JSON parser, because I figure that's, well, anyway, I just did it for fun. Okay, now what's coming out of this is a JSON object. The next thing I want to do is do a transformation where I say, given a JSON object, extract the actual tweet itself and throw out all the other junk that's in there. Usernames, what sort of hashtags are you referencing, what's your location, what does your picture look like, that kind of stuff. So throw all that stuff out. All I want is the tweet itself. Okay, and again, I had this for debugging. And so this will give me a JSON object, and over here I'm going to use the JSON object that they have. They have a select token method, and I'll just say get the text attribute over here. Sometimes it's null, and so if it's null, I'll just return an empty string. Otherwise, I'll convert that text. It's not really text, by the way. It's a JSON token, a J token they call it. So I'll take that J token and convert it to a string. Okay, so that's the next step. And then the next thing I want to do is, given a tweet, I need to break that down into the individual words. Okay, so that means that, let's see. Yeah, so that means given a sentence, a 140 character tweet, I'm going to break it up. So the problem here is I wanted to keep my original string. So I'm going to send as the output of this transform block the original tweet and an array that contains all the words as the second part. And that's just going to be The code is simple. Here's where I say, given a string, create a tuple with the original string, comma, split that string by delimiters. And remember I showed you delimiters is just all the white space, all the punctuation. All right, so that should break it up into a bunch of words. All right, now what I'm going to do is I'm going to take that word extractor so all of these are being linked to. JSON parser is linked to a tweet extractor. Tweet extractor is linked to a word extractor. Word extractor is linked to the branch point. The branch point is a broadcast block. And over here, it tells you, if you have like an object and you say, I want to send this object to a bunch of people or a bunch of other blocks. Well, do you want to send the same object or do you want to send a copy of the object? Or, do you want to, so this is the cloning operation here. And for me, I'm just going to send the same tuple to everybody. So I just say D goes to D, data goes to data. All right, so the word extractor is going to send it to the branch, to the broadcast. Now the broadcast is going to send it to the negative counter and the positive counter. So the same tuple is being sent to the negative word counter and the positive counter. Okay, and they look like this. I'm sure I could have written this in a smarter way, but it wasn't coming to me. This says, given a tuple that has a string and a bunch of words, I want to return a tuple that returns, again, the same tweet with the count. So this will be the negative count, right? And down here will be the positive count. So for each one, it says, and I'm going to get rid of my debugging stuff. So each one of these is it's just going to count the number of words that exist in the negative words dictionary and then put it in the tuple. Finally, we're going to merge all the results in a join block. So I get tuple string int, tuple string int. So things are going to get messy now because the join block is going to merge these two tuples into a bigger tuple. So finally, the output is going to go to an action block, which is a tuple that contains both the negative ones and, the positive ones and the negative ones. And now I'm going to write it out. So it says tweet, the original tweet, the number that I got for positive and the number I got for negative. Okay? All right, now let's just pray that this works. And I'll go over here, switch this to Twitter. And run. All right, well, I can't go backwards. So you see that it's outputting all the tweets, and at the end of it, like here's a, come on. Okay, it's done. So let's look. This one says positive is 0, negative is 1. So why is that? Tweet, Justin Bieber's definition of a break. So it probably looked at break and thought that was negative. Let's see. Let's see. Here's a positive one. Yeah, we have a chance to win a trip together with Justin Bieber at Disneyland. So positive was 1, negative is 0. Let's see if we have a. I thought I saw one that had. Okay, so Justin Bieber can get 20,000 retweets for being annoying. Can we get 5 for Matt being booger free? It says. So something in there was positive, maybe the free, and something in there was a negative, probably annoying. All right, so this is, like I said, this is not the smartest sentiment analysis. It's actually pretty dumb, but wow, somebody just keeps. Okay, here's one. Dream to Bieber. I would kill for another Justin Bieber featuring Chris Brown collaboration. And this is negative probably because it found the word kill in there, even though it's positive. All right, so that is my super stupid sentiment analysis using on Twitter, and it's all using this the data flow system. Okay. Now, you're going to look at this and say, well, that looks messy. I could have just written that as straight line code. Okay. In the real world, of course, you wouldn't have each of these transform blocks listed right here like this. I'm only doing that because it's a demo and I want you to see all the code easily. But in reality, you would write all of these things as different parts of your library. And then you would write something that glues your library together using these transform blocks and the link to operations down below. Okay, so the way that I've written all the code in line, you wouldn't do that. Okay, you would just write a bunch of reusable operations, and then you would piece them together using the data flow system. And that's the benefit of the data flow system, is that it's a very easy way of doing composition. I mean, it's kind of like doing a flow chart, right? Except you're doing it in code. And you can very easily compose all the different operations that are in your libraries, and then you can tell it, I want you to run in in parallel. So, for example, if I wanted to say, well, I want this word extractor, for example, over here. I want this word extractor to use I want it to have a max degree of parallelism. I want you to use 2 tasks. So now I've automatically made it parallel, okay? And we're not going to see any performance improvement here because in this program, the slowest part is actually getting the data from Twitter. The computer can easily keep up. But if I were to get like the floodgate of stuff from Twitter, and I ran this on a big beefy machine, then this sort of parallelism would really help. All right. Let's see. We have only a few minutes, but let me just see if I can get to this other part. So the data flow system is a really powerful system. However, other languages use something called the actor model. Now, the actor model, it's more dynamic than data flow, because in the data flow system, you're creating a network, and it's mostly static. You don't usually like disconnect and reconnect your network while it's running. You usually just set up the network and then pump data through it. With this thing, the actor model, think of it as a bunch of tiny little programs like this running independently, and they're just shooting messages at each other. Each of them has a little queue, okay? And they process data and they send messages to anybody else. And these arrows that I drew, they don't even have to be, they're not hard-coded. So if this guy says, I want to send a message over to here, that's fine. He'll just blast a message over there. He needs to know the guy's name, right? His address. But otherwise, it's pretty easy to do. So each one of these is like an action block, and you use the post method, to send methods to other action blocks like that. And these are called actors. Now, you may have heard of WhatsApp, which is the company that was bought by Facebook for $19 billion. And they build basically yet another instant messaging application, right? But they had several hundred million users around the world. Their entire program is written in Erlang, okay? And they only had like 30 engineers to support, I think it was 400 million users around the world. And they only needed 30 engineers to build this system. Erlang is famous for being just a wonderful implementation of this actor model, because not only do you build these actors to run on a single machine, you can actually build these actors and run them across 100 machines. And when you say, hey, I want to send a message to process number 78, Erlang knows where that process is. It might be on your machine. It might be on a machine in a different data center. Erlang knows, and it will send the message over there. So it's very easy to write these programs. And basically in WhatsApp, each one of these, you can imagine that each one of these actors represents a user. And when you want to send a message, a chat message to a user, you just post the message to that user. And what this guy will do is anytime I receive a message, I'll just connect to that person's phone and send it out. And when I want to send a message, like the user says, say hello to Frank, then this guy will say, okay, take that text, find Frank, post a message over to Frank, and now Frank will put it on that guy's phone, on Frank's phone. Okay? So in Java, there's another library called Akka. Very, very powerful library, really, really nice, which tries to duplicate what Erlang can do. So let me just show you the code now. So here is the world's simplest implementation of an actor, because all it does is it encapsulates an action block. An action block, which is in the Dataflow library, already does almost everything that I need. You give it, like what do you want to do when you get data? So that's what this action is here. And then the only public-facing operation is some way of posting data into that actor. Okay? So let's take a look at an example. So whenever people talk about actors, or even concurrency in general, one of the things they do is they do this ping pong example. Because it's the simplest thing, and all it does is it measures communication performance. So it takes all of your processing out of it and just says, well, how many messages can I process per second? Okay? So in this, I'm going to say, so in this example, I'm just going to use action blocks by themselves instead of the actors. If I use the actors, this would be a lot cleaner. But anyway, I have an action block called ping and pong. Ping is equal to a new action block, and all it does is it says pong.post and increments the number n. Okay? And then pong is almost the same thing, but it's doing the check. It says if n is less than 1,000,000, then post the incremented number back to ping. Okay, so the number is going to bounce between ping and pong over and over again, and it keeps getting incremented. And whenever the number exceeds 1,000,000, then ping will complete, and ping will tell pong that he's complete. Okay? So I started up a stopwatch, and I'm going to measure how long does this take. So this is the ping pong program. And I'm going to run it without debugger. Okay, so this is running on a virtual machine on a Mac, and I've only given it half of the processing power of my Mac. So it took 1.3 seconds to send a million, to do 1,000,000 message sends. Okay, and so if I had given it the whole machine, obviously it would take half that time. And I'm also running GoToWebinar and Skype and a bunch of other CPU intensive things, stealing CPU cycles from this guy. But basically it takes you can do about 1,000,000 messages a second. Well, no. On my machine, you should be able to do 2,000,000 messages per second. You're right, because this is only half of my CPU. So a more complicated example is right here. So if you know what the sieve of Eratosthenes is, it's a way of calculating prime numbers. And what you do is you say, okay, the first prime is the number 2. So if something is divisible by 2, it can't be prime. However, if there's a remainder when I divide by 2, then maybe it's prime, right? So when you iterate, you say, okay, well, how about 3? And it says, okay, 3 divided by 2 gives me a remainder, so 3 must be a prime number. But now I want to add that as the next thing I divide by. So with the number 4, you say 4 divided by 2, the remainder is 0, so it's not prime. 5 divided by 2, the remainder is 1. So let me give it to the next guy. So that guy says 5 divided by 3, the remainder is 2. So this guy must be prime. So what it does is it builds up a chain of all the prime numbers. So I'm going to do that with actors. Okay? So in this example, I have a class called Civ, and what it does is it says divide whatever number somebody gave you by your current prime number, whatever you're initialized as, and if the remainder is not 0, then if you're the last person in the chain right here, then write out that this is a prime number and then create a new actor that contains that prime number after you. Okay, and that's going to be next. So the next time you come over here and you say, wait a minute, I have a remainder, then it says next is not going to be null. It goes here and it says take whatever number that is and give it to the next guy. Let him decide if it's a prime number. So here I'm going to say go from 2 go from 2 all the way to 99 and compute all the prime numbers using this actor model. Oops, I didn't did not change my program around, so oops. Here we go. Start. Yeah, so it produces all the chain of prime numbers, and I think if I hit this, and it's going to be down here, it's too late. If I go over here, let me see if I can stop it there. Yeah, so if I look at 2, it's got a bunch of stuff in there, but I can't get access to its local variables. Okay, I wanted to see what the next was, so we could follow the chain, but it's not accessible. Okay, let me get this down here. All right. Anyway, that is a whirlwind tour. I didn't get a chance to show you MapReduce. I went to all the trouble of writing this program, so let me show you. This is MapReduce, and what it does is I downloaded several big books like Shakespeare, Franz Kafka, a bunch of other books. And over here, what it's going to do is it's going to look at all the books in that C:\books directory that I have, and in parallel, it's going to process the books using this MapReduce function that I wrote up above here. So here's MapReduce. And what it's going to do is the first step in the MapReduce is going to say, given the path to one of those files, split it into individual words. Okay? So the result is, give me a path, I'll give you a whole bunch of words. The next thing it does is it's going to say, group together all of the words by the word. So that means all the thes will be together. Every time somebody uses the word beautiful, it will all be grouped together. Okay? And what I'm going to do is calculate the number of times that the word is being used. So this is just a simple word counter. Okay? So here I do a group. I'm going to group all of those words together by the key, which is whatever word I'm grouping by, and then I'm going to have a count. So how many times was the word the used in all of these books? And then I'm going to take the top 20. Okay? So this is my MapReduce. My MapReduce. All right. So I don't know what this first one is. It must be another delimiter that I didn't filter out correctly. But then the word the is used 51,000 times, of, and, to, a, right? And it takes a while before It'll take a while before we get to an actual, like if I do a take 50, will I get any interesting words? Or is it still going to be filler words? Yeah, so with, which, um, all, who, said, man, been, they. Yeah, lots of filler words. It'll take a while before we get to actual interesting word. All right. All right, so let me just summarize what we covered here. So tasks are, the way to do concurrency on .NET. However, using tasks by themselves is still kind of low level. And so what Microsoft gives you are, they give you plink, which I showed you very briefly with the MapReduce thing, which you basically write a link query, you say .as parallel on your source, and it will magically break up your big link into a bunch of tasks, so it will run using all of your cores in parallel. Dataflow, that's what I spent the bulk of my time talking about, is a way of constructing a network of processing nodes and then feeding data into that network so that all of them start working together. So it's just like a circuit where you feed it electricity. The electricity flows through the circuit, okay? And then actors are a more flexible kind of data flow idea where you're not hard coding the network. Instead, you have a bunch of independent little processing nodes where each one has a queue, and you send data into the queue, and then the actors will act on that information and optionally send data to other actors. Okay, and this actors model, it's very, very popular. There are lots of libraries out there. I haven't found a good one for .NET, sadly, but it's a really great way to write concurrent programs. Okay, so I hope that was useful, and I hope that was exciting. This let me just say that concurrent programs are really hard to write, but it's a really exciting area of computer science right now, and has been for 5 years, because the question is, how can I write these wonderful concurrent programs to make use of huge machines without suffering brain damage, from trying to do it correctly, because it's so hard. And so people are coming up with all kinds of really, really interesting programming ideas right now. These concurrency patterns, right? In order to try and solve that problem. So I've looked at just a few here, and I hope you find this interesting. I hope you find a use for Dataflow, and hope you enjoyed it. All right, thank you very much.